the introduction, Skylar. So hello, everyone. We're Project Prometheus. We're a group of students from the University of Michigan. I'm Alex, a computer science engineering student. Sky?
I'm Sky, also a fellow computer science student. Eric?
My name is Eric. I am also studying computer science. Gabe?
Thanks, Eric. I'm Gabe. I'm studying computer science as well as PP, philosophy, politics, and economics.
And I'm Solomon. I'm studying biomedical engineering. Back to you, Alex.
Thanks, Solomon. So, a brief roadmap of what we're going to be covering today. I'll be providing some context and background regarding our application. Next, Gabe will talk about our methodology as well as the reasoning of why we chose our different data sources. Sky will talk about the data processing aspects of our project. Next, Eric will talk about the machine learning model we created. And last but not least, Solomon will discuss our software development process as well as future plans for the project. So a little bit of context about the app we created. We created Project Prometheus as part of NASA's Space Apps' COVID-19 challenge. So in it, there are a couple of different categories to compete in. We were specifically interested in the human factors category because we envisioned creating an app that would predict disease spread using artificial intelligence. And that category really matched what we had in mind. So an open-ended question to the audience. How would you develop a hotspot index, and what things do you think would be important in identifying a future hotspot? So if you were to, if someone were to ask you, is this county, how is this county doing in terms of coronavirus? What kind of things or metrics would you want to consider in determining like a place's severity? Yeah, so at any time, please feel free to unmute or put in the chat what you think would be useful. Yeah, hospitalization rate, yep. So incidence rates, so hospitalization rates, yeah. So yeah, total testing and percentage of positives, yep. Yeah, so we created a single index based on the incidence rate, mortality rate, growth percentage, as well as total confirmed cases up to the past day. So these are the different metrics that we used because we felt that all these numbers were important in determining, if a county's outbreak was really severe. So Eric will talk a little bit more about this equation later. Yeah. So another question to the audience, how would you predict a hotspot? What kind of numbers do you think are important in determining a coronavirus outbreak? Yeah, mask mandates. Anything else? Yeah, population for the size of area. Yep, urban density. Yeah. So socioeconomic data. Yeah, those are very good. We actually use both of those factors in our model. Yeah, so those are really good. So we specifically looked at environment data, pollution data, health data, ethnicity and socioeconomic data, as well as government action data, because we felt that all these themes were important in predicting if an area was more or less susceptible to a coronavirus outbreak. Next up, Gabe will elaborate a little bit more on why we chose these different data sources. So Gabe, take it away.
Thanks, Alex. So hi, everyone. It's Gabe. And as you can see here on our graph, we have a nice flow chart that details kind of how we had started with the data and then eventually processed all of that data and fed it into the machine learning model. So I'm going to talk a little bit about each data set and why we decided to choose it, our motivations behind it, both conceptual and I guess a little data driven. So I'm going to start on the left and move to the right, starting with the JAXA precipitation data. So we decided to choose this for a few reasons. First, we know when it's raining, people are more likely to do indoor activities. We know that coronavirus spreads more easily indoors with indoor activities. And additionally, we know that there's been some research that it has indicated that areas with higher precipitation have had lower coronavirus case rates. So for both of these reasons, we decided to include precipitation data in our data. Next, I'm gonna talk about the NASA MODIS temperature and UV data. So when the weather is more extreme, we feel that people are more likely to do indoor activities, and this is both hot or cold. Additionally, we know that research has shown that UV rays in higher temperature make it harder for the coronavirus to spread. So again, for both of these reasons, we decided to include this data in our machine learning model. Moving on to pollution, we included NASA OMINO2 NO2 measurements. So, especially we were looking at the US, so we know private transportation is really important to help people get from place to place, like cars and airplanes, which create a lot of emissions. And we know additionally that offices and factories that are open produce a lot more pollution than those that are closed. So especially since both of these are a byproduct of more economic activity, which results in more pollution and higher face-to-face interaction, we felt it important to include those NO2 emissions in our data. Moving on to disease, we looked at the Johns Hopkins cases number. Pretty obvious, obviously more cases means more likely to be a hotspot, so we included that. Both in disease and social category, we looked at the Robert Wood Johnson Health data. So this included a lot of information. It included rates of pre-existing conditions in certain areas, like obesity, diabetes, high cholesterol, smokers. So we know that people with these pre-existing conditions are more likely to have adverse health effects and be more symptomatic. So those areas be more likely to be hotspots. Additionally, it included demographic data like median household income and race constitution of certain areas. So we know that both the factors such as income as well as racial makeup, we know that those areas have been correlated with some certain races have been correlated with higher coronavirus spread and more adverse outcomes. So we decided to include that. Additionally, moving on just to social data, we looked at the NASA SNPP MERS nightlight imagery, knowing that in urban areas, more nightlight, especially in urban areas, more nightlight indicates that more people are awake and maybe interacting with each other, but more importantly, that more businesses are open. And like I mentioned earlier, we figured that generally more businesses means more human-to-human interaction, so greater coronavirus spread. Moving on to the government data, we looked at multi-state U.S. government action data, which gives a value for 1 to 9 for a specific area to indicate how strict or lax a county was when it came to lockdown restrictions like mask requirements, business closings, etc. So conceptually, we know that those areas with stricter lockdown restrictions will result in people going out less and interacting less, and then vice versa for more lax restrictions. So that would obviously factor, we thought, into coronavirus spread. And then lastly, we looked at COVID tracking project testing data. So just looking at testing. Again, this is kind of a chicken and the egg, since we know it's a problem because we know aggressive testing and tracing will lead to finding more cases in areas, so more likely to be considered as a hotspot. But we also know that if an area has more coronavirus cases, more likely to start testing at greater capacity or start testing at a greater clip. So we decided to include that data. After we processed all of that data, mostly using pandas, as well as some other conversions, we were able to basically merge all of that into one data frame, and then which Sky was able to do, and he'll touch on that in a bit. And then Sky was able to pass that data on to Eric, who was able to create a long short-term memory model, machine learning model to determine potential future hotspots. So Eric will talk about that later. But for now, before I pass it over to Sky, I just want to show quickly a few maps that we were able to use and that we drew our data from. So as you can see here on the top left, we have a map that depicts states open, closed, or with certain restrictions. So again, this kind of pertains to the government data. On the bottom left here, we do have a GIF that indicates a time lapse for night capture. So as you can see, it begins earlier, and you can see that there's a lot of night light, but over time, especially as lockdowns were initiated, the amount of light goes down significantly. Top right here, we can see the global temperature data, and then the bottom right, we can see the precipitation data. So I think that's enough for me on our methodology and our motivations behind the data we gathered. So now I'm going to pass it over to Sky. He's going to talk a little bit about the data processing. Sky, take it away.
All right, Gabe, thank you for your presentation. Moving on to data preprocessing, we had to work with many types of data sources in the form of CSV files, HE5 files, and others. For example, for HE5 files, which contained daily data on NO2 emissions, this belongs to the category of pollutions, we extracted the data we needed array, where the dimensions of the array were latitudes and longitudes, and the array values indicated the concentration of daily NO2 emissions. Because the array was lacking in actual longitude and latitude coordinates, we had to use a geodata file, which converted the coordinates to counties and states, and then we used this data to create the corresponding columns in our new data frame. Next slide, please. To go from latitude to longitude and longitude coordinates to the indices of the array, we had to use some simple arithmetic so that we would know which counties and states corresponded to each individual array value. At this point, after we pinpointed the NO2 emissions, the daily NO2 emissions for individual counties and states, we use these corresponding columns in our new data frame, the counties, the states, and the date times to update information in our main data frame. Next up, I will pass the presentation to Eric, and he will explain how he would use the main data frame to create a machine learning model.
Yeah, thank you, Sky, for explaining how the data is processed. So once we have all this data ready, they're ready to be taken in by the machine learning or ML model. So the model can take in any time range of data. So for instance, maybe 2 weeks or maybe just 1 week of worth of data, and it's going to predict the following hotspot index, say a week in advance or 2 weekends in advance of every county in the United States. So again, the hotspot index equation shown here, some of the methodology going into it, like the use of natural log here, is because I want to normalize the data that is skewed by number of cases in some counties. So for instance, in New York, we have maybe like hundreds of thousands of cases, and maybe in some counties only have like tens of hundreds of cases. So that's just to kind of normalize the index. And that's what's going behind the reason why we develop the index in this particular way. Next slide, please. So the model we used specifically was a long short-term memory model. It is a machine learning architecture that is great for time series data. It was made with TensorFlow, which is an open source machine learning library. We followed a tutorial on their website. I've attached the link down below on our slide. If you're interested, please go check it out. The model is trained on Google Colab, which is a free Python-enabled environment on the cloud that allows you to run Python code without having to install anything locally. So it's great for running machine learning models. Lastly, once we have the model trained, we use permutation and perturbation to determine what are the most important factors among all the data we just discussed when it comes to our model's prediction. Next slide, please. So this is the perturbation results. So what perturbation is, essentially we randomly add a value to each of the factor to see how that affects our model's performance. So if we change one specific factor by a little bit and the model starts to perform really bad, then that means that factor is probably important, very important to our model's prediction. So as you can see here, at our top factors are the total number of test results, number of deaths, and surprisingly, the percent of African Americans, number of populations, mass mandates, percent of Hispanics, median household income, et cetera, et cetera. So as you can see, some of the socioeconomic data are actually on the top here, and some of the environmental data are actually towards like the bottom and not as important to our model's prediction, most likely due to the fact that some of the data was not exactly real time, and some of them was used for historical data. The next slide, please. Next, we have the permutation results. So what permutation does is it randomly shuffles each factor and try to see how that affects our model's performance. If our model does worse when we shuffle a specific factor, then that means that factor could be important to our model's prediction. And again, we have the percent of African Americans, total number of test results, number of deaths at the top factors here, and some of the environmental factors are towards the bottom again. Just very interesting results from our model's performance. And next we'll discuss how the whole process was done and managed, and we'll pass it on to Solomon. Solomon, take it away.
All right, thank you, Eric, for giving us a description of the back end. So for the front end, we wanted to create like a nice graph, like a map, so that we could be able to show or demonstrate where the hotspot regions were. And by utilizing Leaflet and JS, we're able to create a choropleth, which is what you can see on the top right. It's just a place where we could index and show where hotspot regions are and where specific areas of focus are. And then that was used by mapping out population index cases to the 1,000 and GeoJSON files from the internet. And then in order to conceptualize the rest of our data and to demonstrate our graphs properly, we created a website using HTML and CSS. Next slide, please. So the development method that we use specifically in this whole process was the Agile method. So the Agile method is a very popular method now used by a lot of corporate world, because it is a method where software developers or any developers in general can be able to stop at a specific area when they see that there's an error and just move on. And specifically in this process, we had our daily stand-ups, so we could talk about if there's any roadblocks, so if there's any issues. So let's just say if Gabe had a specific question or any problem, we could, as a team, help him and supplement in these issues and areas. And during the Agile process, there's also sprint planning and the backlog grooming. And specifically in our portion, since we didn't have a lot of the technical aspects for it, we use an Excel sheet to be able to document. So on the bottom right, we can see all the tasks that we had and the specific people that it's assigned to, and once it's completed, and the specific links that we had to it. So this allows us to keep track of how everyone's doing and what everyone's working on, and in order to keep our project in motion. Next slide, please. So in the corporate world, it's usually used by the Jira board and the Confluence page. So what a Jira board does is a Jira board tracks the specific tasks, stories, epics, subtasks, and sagas that are being used. So under this circumstance, we could be able to create ideas of what is completed and what isn't completed, and assign different storing points by assessing how hard a specific task is. And then if there's a specific documentation that we needed and everyone needs to see, we can be able to place it on Confluence so that everyone can be able to specifically map out what's going on and where to see where everything is at. Next slide, please. So for future developments, we want to make a data pipeline to collect real-time data from NASA, Johns Hopkins, and other data sources. And the main reason why we want to do that is we want to continue to make predictions and to keep the model up to date and to improve the model accuracy. And since we want the data link, we plan on continue using the data link to continue to enhance our development. Next slide, please. And as Project Prometheus and Team MRC, we would just like to thank you guys for your patience and listening to our presentation. If there's any questions or if you want to contact us, here's our information and pictures. Thank you.
Yeah, so I think we'll open up the floor to any questions. I think there's already a question from Ping Wang. I think this is a question for you, Eric. She's wondering why we used an LSTM model instead of a GRU model.
Mm-hmm. Right. Great question. Thank you, Wang. So at the time, we didn't really, we just looked at a few models that might be good for time series data. While we wasn't really aware of the GRU model at the time. It's like a relatively new architecture. However, yes, GRU could be more efficient in cases where the data is not very large, and we wouldn't want as accurate results as possible. LSTM, on the other hand, is great with when there's a lot of data and we want it to be as accurate as possible. So that's why we kind of go with LSTM. But yeah, if we had the time, we would have probably experimented with GRU as well to see how that performs. But yeah, thank you for the question.
Hello, this is Greg from UNLV. I have a question about the normalization index, right? That's how you call it, normalization factor. So does that incorporate like different testing methodologies in different countries? Like this happens in Europe, every country has different, even with different tests. So does that include?
Sorry, I wasn't able to hear it very well. I just heard you talking about different countries, right? Is that a question? Yeah, because there's a lot of like background noise. Or maybe you can type it out in the chat. Yeah, thank you. Okay, so yeah, the question is, does it include different testing methodologies for different countries? So for our study and for our project, we only included the United States counties. So we didn't really consider any other nations for our particular project. So yeah, I hope that answered your question. Yeah, thank you. And then we have another question from Wang. How did you avoid overfitting in your project? So we had some layers in our machine learning model that tries to encompass the overfitting side. While we closely monitor the validation, while we use the train validation split, essentially what it does is we try to take a certain portion of data, training data out to evaluate how well our problem model does on that portion of unseen data. So if our model does very well on the training data, but it does poorly on that evaluation data, then we'll know something is wrong, that model is overfitting. So we closely monitor that to make sure the validation accuracy and the training accuracy are about the same, or going down throughout the training process. And we also added some dropout layers to filter out some noise in the data set. And yeah, that's essentially how we avoided overfitting in our project, in our model, machine learning. And that was getting a little bit technical with the machine learning model, but yeah. Oh, okay, another question. Explain the idea behind the Atom optimizer. Okay, so for the machine learning model, we use the Atom optimizer, and essentially it's one of like the most like popular optimizers among others for machine learning nowadays. So we have others like stochastic gradient descent.
Stochastic, yeah.
Stochastic gradient descent, sorry, and a few other ones like RPMs, RMS prop. So we just chose Atom because experimentally it does perform better. For our particular project, I tried other models. I tried RMS prop. I tried a few other optimizers, and Atom just performs better than the other models. So that's the reason why we go with it. Yeah, thank you for the question. Any other questions? think someone else can take this question from Christopher. Maybe
Sure,
Solomon.
yeah.
Or
Oh, yeah.
Alex.
Yeah, I can take this question. Yeah, so kind of the backstory behind our team is that we're a group of friends. So most of us were studying computer science. Eric actually introduced the hackathon to the rest of us. And we essentially wanted a team that had, I guess, a variety of different skill sets. So as you may have noticed, Eric's main strength is in machine learning. He's done a lot of, I guess, he's had a lot of practice with creating different machine learning models. For me, it's mostly in full stack and web development. So while I did a lot of the data processing work, I also was able to help with creating the UI for our website that we have. And yeah, and also Sky had a lot of experience doing data processing. So same with Gabe and Solomon, we also included because we wanted an outside perspective that was different from, I guess, a group of computer science students. So yeah, we wanted to make sure that we essentially got a group with a variety of different skills. But yeah.
Are you aware of the MIT group's COVID analytics data sets? What do you think of those data sets?
Okay, I'll take that question. So at the time, yeah, we weren't aware of the COVID analytics data set. So I can't really comment on that. But yeah, we'll definitely check it out afterwards to see what it looks like and how that would help with our model.
So what do you think are the next steps in this project?
I think I'll take this one. So for the next steps, I think we want to continue to improve our machine learning model, like as we said towards the end. And I think we maybe want to expand on different countries too, since we have a pretty nice built model for the US. We think that even though like some news source may say that other places may have lower rates, maybe being able to contact what hotspot means in different parts of regions can be able to further our development as a group for this project. Thank you for the question.
Yeah, just to add a little bit on that, one of the things that we wished we could have done is made our model actually more real time. Right now, it's just static. It makes a single prediction. So we're probably going to look into using AWS services to make our model a little bit more responsive, so we can collect data, daily or weekly, and update our predictions that way. Because right now, it's, I think, just making a single prediction for the month of May, or in the month of May.
How much of what was presented today was complete at the end of the challenge versus continued work afterward?
Okay, I'll take it. So essentially all of this work is mostly done. It's all done like by the end of the challenge. So we had like 48 hours to complete the challenge, and that's most of the work you see here is completed during that time.
Yeah, and to add off of that, Eric, I think one of the things we found that was really helpful was to try and, I guess, be familiar with the platforms we're getting the data off of, because data processing was probably something that took the most time. So before the hackathon started, we looked a little bit at how the data was formatted. We didn't write any code, but we did look at what things we would need to do to get the data. So we planned out the tasks that we would need to do during the hackathon very well, which I think allowed us for very rapid development.
I wonder if it is a fair way to build a universal forecaster to predict for different counties, because each county has a different number of population as well as the infected over time.
Right. Okay. Yeah, so that's the reason behind why we built the hotspot index, since each county has like different number of population as well as infected over time. So that's why we took consideration of like the incidence rate. So that just takes care of the population. again, the mortality rate as well. They're all in efforts of trying to normalize, taking into account the population for across different counties and the number of cases as well, to bring them down to about the same scale. Yeah. And hope that answered the question. Yeah.
Have you thought of adding a clustering algorithm to see if you could track which areas were most vulnerable?
Yeah, I'm actually glad you asked that question. That was actually one of the things we were planning on doing, is doing some clustering to identify, common, common clusters or groups between the different counties, and to see any patterns there. So yeah, we actually were looking at doing that, but due to the hackathon's time constraints, we only had 48 hours, so we weren't able to quite reach that goal. But yeah, that was something we're planning on doing.
So the next question was like, how powerful are your computers? Our computers are just regular PCs and Macs. I don't really think you need a supercomputer in order to do this, but our computers are PCs and Macs.
Yeah, and add on to that, we used for the machine learning model, which we used the Google Colab, which is a pretty much like a cloud computer that you can use for free. So you have access to GPUs in the cloud, so additional computational power. Yep.
Some of our students are new to machine learning. Would you advise on how to learn how CNN, RNN, and LSTM work?
Right. Okay. So yeah, there's a lot of great tutorials out there on the internet. I suggest to just check it out. I think it's like a website called Machine Learning Mastery that has a lot of good tutorials and introductions to people who are first timers to machine learning. There's a few other websites. The TensorFlow website itself was great. The tutorial that I had in the slides. Scikit-learn, Alex just had attached a link to the chat, and PyTorch, those kind of things. YouTube tutorials helps as well. But yeah, just the internet is a great source of a great resource to learn machine learning. And if you have more questions about machine learning, you can shoot us an email, and we'll point you to the right resources.
What advice do you have for first-time participants doing the 2020 challenge?
I think I'll take this one. So the NASA SpaceX challenge was my first one. And I think just keeping an open mind and like being willing to learn new things that you don't know. Like for example, web development. Like I know Alex says he worked heavily on it, but being able to like learn and like being a part of it was a really big challenge, because I'm pretty sure everyone in our group tried to push past the border of what we knew in order to create something that we didn't know we could create. And I guess that's the biggest advice I'd have for people who are doing it for the first time.
Did you pick TensorFlow because of its tools, large user base, performance, or some other factor? Do you think another library might be worth exploring?
Yeah, okay, I'll take that. So definitely we're thinking about using other libraries such as PyTorch at the time. But when it comes to like LSTM specifically, I was just trying to find tutorials, and I just found that the TensorFlow tutorial is the easiest to follow, and also have previous experience working with TensorFlow, so that just help us to get the project done in a timely manner due to the 48 hours time constraint. But definitely, other libraries are worth exploring for sure.
So you think of forecasting after time series clustering as a better approach?
So forecasting after time series clustering as a better approach. So I guess the question just asking, is forecasting, because like forecasting and clustering are like kind of two different things, right? Clustering, you're trying to see what are the patterns in the data and see where are the hotspots currently. or forecasting is you want trying to predict a future data. So like, so I'm not sure if I understand the question. If you can maybe rephrase it, or
do you think of forecasting after time series clustering as a better approach? Maybe. What are the alternatives to LSTM?
right? Okay. Alternatives to LSTM. There's also, non-machine learning stuff that we could use. It's definitely like linear regressions, just regular regressions, logistic regression, seasonal moving average prediction. I think there's like a algorithm called ARIMA. There's a bunch of statistical approaches that could have been investigated that are just outside of machine learning. And inside of machine learning, that's just, as you mentioned, GRU was another alternative when it comes to machine learning. Just a lot of things we could have explored. But again, due to time constraint, we just went with LSTM.
Why is my model training on one epoch takes 2 hours? Why does my model training on one epoch take 2 hours? Sorry.
Yeah, no problem. Okay. Yeah. Well, I'm not sure what model you're referring to that you're trying to build. But this could be due to different reasons. First, your computer, it's computing power. If you don't have a GPU, then things could take a while to train. Second, if you probably want to look at your architecture and see the number of neurons, if there's too many layers to your machine learning model, if your model is too complex, essentially. But yeah, or your data size is very large, or the number of batch size for each iteration of training is too large. That could also be another factor. But yeah, I'm not sure which model specifically that you're training, but those could be the factors affecting the training time.
Are you going to update this project?
Solomon, do you want to take this question?
Oh no, you can take it.
Okay, yeah. So, yeah, we definitely would like to update this project, but due to the semester, we're probably going to be a little bit busy. But yeah, we do plan to make a return and at least try to develop something off of this. Yeah. So the short answer is yes.
Okay.
Oh, yeah, I can
As-
take this one, I guess. So go ahead. You can read it.
Okay. As far as I know, some teams got funded after winning the Space Apps Challenge, like Sky Watch, but most teams just gave up. Any comments?
So I guess one of the things I can speak from personal experience is obviously working on the hackathon was pretty time consuming for all of us, and it was I had to, at least for myself, I know everyone else on the team did as well, take time to learn a lot of new concepts that we hadn't used before. I worked a lot on the Core Plus, so I was working, basically learning a lot of JavaScript, trying to learn different JavaScript architectures as well, such as React. Just ended up using JavaScript at the end of the day. And that takes a lot of time and effort. So if it's not something you're actively thinking about, or if there's not a deadline that is there kind of to push you forward, I know that a lot of us had internships as well, so we were working full time during the week, and then I know, at least for me, on the weekends I like to relax and just spend time hanging out with my family and friends. So having that motivation is something difficult, so I'd be surprised as to why that's why a lot of people don't necessarily continue with their projects, especially if you're coding already for a large portion of the week. So that's my belief, at least.
Is it possible to extend this exercise to other infectious diseases? Sorry.
Okay, yeah, before we go to the next question, the only thing I was going to add to the previous question was that as far as funding goes, we did receive some, like, I'm not sure if I would call it funding, but we did receive, I guess, the Data Cube Award. So what that basically allows us to do is use the European Space Agency's data processing platform to help us process data, but we didn't really use any data from them. So yeah, we haven't received much funding to continue the project, but I think we'll likely try to do something just based on our own interest.
To answer the next question, is it possible to extend this exercise to other infectious disease? I think that's a very abstract and hard question to answer, because every disease has its own biological like influential changes that it may possess. But I think using this challenge, we may be able to use past data and maybe to continue to improve our model for the future. But I don't think we can extend it for like future infectious disease, but maybe for the past. Maybe it might be able to help the past.
Would you like to
Oh.
comment on the saying as machine learning is more hype?
Yeah, I actually have some hot takes on this. So yeah, so I took a data mining class last semester, and machine learning definitely has its place. But I guess what you have to be wary of is not trying to use a hammer for everything. So machine learning is great. It definitely helps make predictions in many instances, but there are instances where machine learning does have its limitations. Like if you're trying to make quick and rapid predictions, machine learning models typically take a while to actually build and produce. And there's some, I guess, trends that existing statistical methods already do a good enough job of predicting. Like, for example, in the stock market, a lot of people are trying to use machine learning there as an application to try and like predict prices and whatnot and future stock market trends. But it turns out that linear regression is actually a pretty good model. So yeah, I think machine learning definitely has a lot of potential applications, but it's not a one-size-fits-all tool. So yeah.
Do you
Alright,
think
I guess I'll
statistics?
give.
Sorry. Do you think
Go ahead.
statistics department will disappear and someday will be machine learning department?
I feel personally that statistics is a big part of machine learning, and especially behind the data and all that. But statistics will not be replaced by machine learning. Machine learning by itself is a special topic. It is used to make predictions, other things of the sort. But statistics covers a much wider field. It goes through sampling, surveys, probabilities, all of that sort, which are things that machine learning might touch upon, but not necessarily. So machine learning is more like a subset, a proper subset of statistics, and statistics is like the the overarching the overarching category, the support behind machine learning.
Yeah, just to add on to that, hi everyone, it's Gabe. Yeah, especially for statistics often covers fields like, if I think personally, I obviously am a part of one of my degrees is politics, and I follow politics in the U.S. pretty closely. So knowing how important polling is, especially if you think about 2016, when a lot of people were talking about polling and accuracies in polling and how important that is, it's pretty hard to predict things like polling averages, especially when it comes to politics. The factors that play into a candidate's popularity or unpopularity aren't really that predictable. By machine learning, I would say it's pretty, it can be pretty fragile or pretty fickle in terms of, or not make that much sense in terms of why a certain candidate is popular when it's unpopular. So replacing that with machine learning would be pretty tough, at least in the near future.
Just one last note on first timers in entering hackathons. For our team especially, we did spend a little time on like researching beforehand. So we looked into like what kind of factors that might have played a role in the hotspot indices. We went through many data sources provided by the hackathon, and we also went online and searched up for many other data sources as well. And doing that work ahead of time helped a lot, especially when the hackathon began and we had like tight time constraint. So doing a little research beforehand would really help in giving you the upper hand in a hackathon. Mm-hmm.
Yeah, just to add on to the hackathon, I guess if you're doing a hackathon for the first time, sorry, I took my camera on, there we go. At least something I realized is when I started the hackathon, I hadn't really done much JavaScript before. And I took a security class, so I was doing like some small attacks in JavaScript, just practicing for that, but no like actual larger programs. I know they had a tutorial for React.js, and I tried to use the React architecture for JavaScript, and I couldn't figure it out. So I had to take the time to learn that, as well as learn how to use Leaflet, since I was creating the core class. And it was pretty daunting. At one point, I felt like I couldn't finish everything in time because we had only about maybe 24 hours left, and I still didn't have a core class up and running. But I guess just make sure that you persist through with your work and keep working, keep trying at it, even if it feels like you might not be able to make a good solution at the moment. I would just keep driving at it, because that's definitely how I felt. Like we might not have a core class at the end of the hackathon, but I think that was kind of like a thing that took our machine learning. Obviously, the work that Eric did and Sky did and Alex did with data processing was impressive, but being able to visualize that and have it be very clear as to what the data was saying, I think really put our project over the top. So I would just say, believe in yourself and keep pushing through, even if it seems like you're not going to have a good result.
Yeah, it just add on to that, not just for the crawler path, and the machine learning model itself was actually almost didn't come into existence towards the very end of the hackathon, because the training error was just through the roof for almost like in the first half of the hackathon or so. It was just getting very, very large error, and I was spending a lot of time trying to figure out why. And that's just a big part to machine learning, really, just to playing around with your model and trying to figure out what part of the model could be wrong. So in our case, it was not using the correct number of neurons, or not normalizing the data correctly, so which causes it not to converge. So there's a lot of persistence that you need to, especially when it comes to machine learning and in general in doing these kind of hackathons and projects. Yeah.
Thank you, Alex, Sky, Eric, Gabe, and Solomon. Thank you very much for your presentation, and thank you for sharing with us your time and expertise. Thank you, everyone joining us today, for being attentive and asking good questions. We hope to see you again. Bye.
Hey, thanks everybody. Just want to say this quickly. Thanks to everybody for attending and asking questions. We really appreciate it. We love sharing our work with others and our expertise. So really appreciate everyone joining in.